Well, in this session, we'll be working on the simulation of distillation processes. Previously, we have recorded separate videos for the property analysis, simulation of pressure changing equipment, simulation of heat exchangers, simulation of non-kinetic reactors, and single stage phase separators, including two-phase separator and three-phase separator. From now onward, we'll be working on the simulation of multi-component, multi-stage separators, including distillation, absorber strippers, and liquid-liquid extractors. Specifically for this session, our focus will be entirely on the distillation columns of multi-component systems. I have recorded a separate video for the detailed background on the simulation of distillation columns, including different unit operations available in Aspen Plus, key terminologies related to the distillation processes, details of the column internals, shortcut methodology for the design and rating of the distillation process, even the internal details of the tray columns and pad columns, and even problems that may arise for the column operational feasibility. But for this specific session, we have a case study of the distillation trains for the separation and purification of the products of ethylene glycol production process. So the case study is ethylene glycol is produced by the reaction of ethylene oxide with water, forming different grades of ethylene glycol, including monoethylene glycol, diethylene glycol, triethylene glycol, and tetra-ethylene glycol. In the ethylene oxide hydration process, ethylene oxide reacts with water to produce monoethylene glycol that further isomerizes with the ethylene oxide to produce diethylene glycol. Diethylene glycol reacts with additional ethylene oxide to produce triethylene glycol, and similarly triethylene glycol reacts with ethylene oxide to produce tetraethylene glycol. So at the reactor exit, we have unconverted ethylene oxide, water, and the products of ethylene oxide hydration process. So the complete process of the production of ethylene glycol involves three key steps, including the reaction, drying evaporation, and separation purification of the ethylene glycol products. The sequence of these process steps is shown in figure 6.3. Here is the figure where we have the reactor section, multi-effect evaporator section to remove excess water and recycle back to the reactor inlet, and the purification separation section. This case study specifically emphasized on the glycol separation section, where the leftover water is first removed from the distillation column that is termed as dehydration column. The ethylene glycol rich stream follows three distillation columns. In the first distillation column, monoethylene glycol is recovered as the top product. In the second distillation column, diethylene glycol is recovered. And in the third distillation column, triethylene glycol and tetraethylene glycols are recovered. So the feed to the distillation column includes the ethylene glycol products and water. This water is left over from the evaporation section, so we have to recover it from the first dehydration column. The flow rates of the reactor exit are given. Temperature is 160 degrees Celsius, pressure is 4 bar. Property method of CPA is also suggested. The details about every column is provided in this table. For instance, in the first dehydration column, we are asked to use equilibrium based calculation. The number of stages, reflux ratio, and reboiler duty are not provided. Rather, we are asked to use a shortcut model to first determine these parameters and then use these parameters for the rating with appropriate column internals, where the column internals as a packed bed is also given, along with the section height and the column diameter. Similarly, for the ethylene glycol columns, these specifications are provided, and some of the primary design parameters have to be obtained by using the shortcut approach. The overall objectives of these simulations are to develop a separation process scheme for mentioned product recovery and purity. Product recovery and purity are given in the above table. Determine the design parameters such as reboiler condenser duties, reflux ratio, pressure drop of the distillation column using the shortcut approach, and validate the parameters using rigorous approach. And then we are asked to study the column profiles of composition, temperature, and pressure, and also asked to study the column performance for the rating purposes. So let's open Aspen Plus and develop the separation scheme for the purification of ethylene glycol products. So let's open Aspen Plus without any default template. First, enter the components. So the components involved in this simulation are diethylene glycol. We can find diethylene glycol with the name TEG, then water, ethylene glycol, triethylene glycol, and tetra-ethylene glycol. For tetra-ethylene glycol, we can just copy this name and search from the component name. So we have 14 components with the name tetraethylene glycol. Let's put the search criteria to equal to tetraethylene glycol, and we have only one component. Let's add the component and rename as for EG for better recognition. Let's move next to define the property method. For the property method, we are already given with the name CPA. CPA is the cubic plus association equation of state package. Let's move forward. So these are the binding interaction parameters for the CPA method. In fact, we would have all the combinations of the binding interaction parameters, but by default only 3 combinations are provided. At least the interaction parameter of water with the tetraethylene glycol is missing. So let's stick to the default, otherwise we should have either the missing parameters by regression, or we can manually embed all the binding interaction parameters of the missing pairs. So let's move forward, and with this we can run the properties environment. So let's save this file before moving into the simulation environment. Let's switch to the simulation environment. First, define the feed stream. Let's name it as feed. Enter the specifications. Temperature is given as 160 degrees Celsius and the feed enters at 4 bar pressure. The mass flow rates are given. Let's switch to the mass flow rate and enter all the values. So the feed stream is defined. Next, we have to define the flow sheet. For the flow sheet, we need to use the regress distillation column, that is a RADFRAC column in this case. But before that, we have to determine some key design parameters, including number of stages, reflux ratio, and the duties. So for that purpose, when we don't have any of the information available, we can use the shortcut approach. For the shortcut approach, we can use this shortcut design distillation column that takes advantage of Fensky-Underwood-Gilliland or Wien-Underwood-Gilliland method. That is the first shortcut design unit operation. And then for the rating purposes, we have the unit operation with the name DISTL that takes advantage of the administer method to perform the shortcut distillation rating. And then we have the rigorous 2 or 3 phase distillation column with the name RADFRAC. And then remainder unit operations in this model palette are the liquid extraction columns, multi-frac distillation column for the complex simulation purposes, and some distillation columns for the petroleum refinery. So let's first use the DSTWU column to determine the design parameters. Let's name it as column 1 DSTWU. So connect the feed stream with the shortcut and connect the products. So the DSTWU column can only have two product streams, one as a distillate product and the other as a reboiler product. As an optional, we can use a condenser decant water stream that is not required in this case. So let's use the top product stream, name it as shortcut top 1, and similarly the bottom product stream as a shortcut bottom 1. Let's enter the column specifications. For the DSTWU, we have to provide either number of stages or the reflux ratio. One of these two parameters is required. Then we have to define the light key and heavy key components in the distillate product and the pressure in the condenser and reboiler. One of the common approaches, if the number of stages are not known, then we can take advantage of the minimum reflux ratio. By default, the Fensky-Underwood-Gilliland method determines the minimum reflux ratio and minimum number of stages. For practical cases, it's very common to take 30% more reflux ratio than that of the minimum reflux ratio. If we have a certain percentage of the minimum reflux ratio, then we can take a minus value. So minus 1.3 means 30% more than the minimum reflux ratio. So if the number is positive, that should be taken as the exact reflux ratio. Then for the key components, so for the first column, since this is a dehydration column, as a top product, the priority will be the water, and any component heavier than water will be taken as the heavy key component. So it's required to recover 99.96 weight percentage of the water in the top product. So the recovery is 0.9996. So this number actually means the light key component in the distillate. So that is taken as the moles of light key in the distillate by moles of the light key in the feed. So that means 99.96 mole percent of the feed water will be recovered from the top product. So this is a mole percent. Actual required is the weight percent. Will rectify it afterward. For the heavy key components, as of now we are not sure which should be the heavier key component, but let's take advantage of the heaviest component of the available 5 components. Water has the least boiling point out of all the 5 components, and tetra-ethylene glycol has the highest boiling point of these components. And we need to define the recovery of the heaviest component, and this recovery is not the recovery in the reboiler, rather this is the moles of the heavy key in the distillate rather than reboiler divided by moles of the same component in the feed stream. So by virtue of the definition in Aspen Plus, this heavy key component recovery in the distillate should be the minimum. Let's take a fair value of 0.001 as of now. So this recovery also indicates the purity of water in the top product. The pressure in the condenser is given as 0.15 as a top stage. Reboiler pressure is not known so far. We can fairly assume no pressure drop as of now for preliminary calculations. So these are the minimum requirements to run the shortcut distillation design column. Let's run the simulation. We have the error. Let's check the error. So error is minimum reflux ratio calculated from the Underwood equation is much lesser than the reset value of 0.1. So let's skip this error as of now and move on to the products. The top stage temperature is 63.7 degrees Celsius and the reboiler is 144.9 degrees Celsius. So let's move on to the mass flow rates of the two product streams. So water recovered as a top product is 34044.3 kilograms per hour. That should be 99.96% of the total water entering in the feed stream. So that is much appropriate. However, the problem is the purity of the top product is not water. Rather, it is only 32% by mass and 61.8% ethylene glycol is leaving from the top product. So that is the total loss as of now. So that is primarily because of the definition of heavy key component in the input. Let's change the definition of heavy key component from the tetra-ethylene glycol to triethylene glycol. And before that, the mass flow rate of ethylene glycol in the top product is 64970. Let's run the simulation once again with a different heavy key component definition. So now the ethylene glycol loss in the top product is nearly half of the previous value, but still this is a lot of loss of ethylene glycol. We can still switch the definition to diethylene glycol and see the loss once again, and this time the loss is reduced a lot further, but still let's shift the definition to monoethylene glycol. With the monoethylene glycol definition as a heavy key component, the loss is reduced to 67 kilograms per hour. So in order to check what is the percent loss of ethylene glycol, let's take 67.02 by the flow rate in the feed stream 67021.4. So 0.001, that is the definition we have provided as the recovery of the heavy key component in the distillate product. So 0.001 or 0.1% of ethylene glycol leaves along with the water in the top product. And we can check the mass fraction. So 99.8% is the purity of water in the top product and remaining is the ethylene glycol. We can also check the results. In the results, we have the minimum reflux ratio, actual reflux ratio, the number of stages minimum required is nearly 4 stages, and the actual reflux ratio to this actual reflux ratio is 37.2. So nearly 38 stages are required. So in actual column operation, 38 stages for ethylene glycol seems quite high number of the stages. So this is a matter between reflux ratio and the number of stages. We can increase the reflux ratio to reduce the number of stages at the cost of the operational cost. Higher number of stages means higher capital cost and the maintenance, but lower number of stages will require higher reflux ratio, mean higher operational cost. So we can slightly check with a different reflux ratio of, let's say, 0.3. As of now, we are not sure what should be the reflux ratio and minimum number of stages. This is entirely a matter of column optimization. But let's have a look with the reflux ratio of 0.3. The number of stages is reduced from 38 to 8. And similarly, the reboiler and condenser duties are adjusted. We can stick to this number as of now, and we can recheck the same in the regress method. Distillate temperature is 54, bottom temperature is 143, and distillate to feed ratio is 61.9%. And we can cross check once again the products in the distillate product and the reboiler product. So in the distillate, we have still 99.96% recovery of water, and 0.001 is the recovery of ethylene glycol in the top product. So at least with this preliminary simulation, we have some of the primary design parameters. Another option is if we want to determine how the reflux ratio and the theoretical stages are affected, we can check this option to generate the table of reflux ratio versus number of theoretical stages, and we can run the simulation. Even we can provide the range of the initial to final number of stages. It doesn't mean the exact number of stages, rather this is entirely a theoretical parameter to determine the relationship between the reflux ratio and the theoretical stages. So this is how the number of theoretical stages and the reflux ratio varies from the minimum reflux ratio of 4 to onward 30. So that is the relationship. We can even plot and have a look how visually this relationship looks like. So let's stick to these design parameters, and then we can move on to a rigorous distillation column of RADFRAC. Let's take a RADFRAC, name it as RADFRAC column 1. For the products, we can give a vapor distillate product for the RADFRAC, a liquid product same from the condenser, and a bottom product. These are the minimum required product streams. Optionally, we can give a second liquid phase for the decant water, a side product stream, and the pseudo product stream. So let's use a distillate product in the liquid phase, name it as RADFRAC top 1, and similarly RADFRAC bottom 1. For the feed stream, either we can define entirely a new feed stream, or we can take advantage of a manipulator. There is a block, duplicator block, that takes the feed stream as the inlet conditions and reproduces the duplicates for the product streams. So name it as duplicator 1. For the duplicator 1, we can give the inlet stream as the predefined feed stream, and from the output we can give one product stream to the shortcut distillation column, and similarly one product stream to the RADFRAC column. So let's enter the details of the RADFRAC column. For the RADFRAC column, we will require the results of the shortcut column. From the shortcut column, we had 8 number of stages. Let's use 8 number of stages. Keep it as equilibrium mode. Otherwise, we can run the RADFRAC column as a rate base. Rate base is generally required in case of the separation system that is too far from the equilibrium conditions. These are two different modes of calculations for the distillation process. So let's stick to the equilibrium based calculations. We can use total condenser over here. Reflux ratio, we can take the same as from the shortcut of 0.3. And the second specification required over here, we can give the reboiler duty. This is a very common approach to define one specification in the stripping section and one in the rectification section. In the reboiler duty, we can take advantage of the same reboiler duty. Let's shift it to megawatt. Otherwise, we can change the units to default calculate the duties in terms of the megawatt. Let's first switch to some other units and then change the system of units. For the default metric units in temperature and degree C and bar, let's change the units of enthalpy flow to megawatt and select the defined metric bar unit system. So by default now The units are in megawatt. Let's enter the value of 24 and also open the shortcut distillation product results. And then we have to define the stream specifications. For stream specifications, first is the feed stage. The suggested feed stage is above 4. So let's take above 4. And the pressure requirement is, the top stage pressure requirement is 0.15, and we can keep the section pressures or the bottom stage pressure as empty. So these are the minimum requirements for the RADFRAC column. Let's run the simulation. We can view the results. So the temperature of the top stage is calculated, condenser duty is determined. So the condenser duty in RADFRAC is calculated as around 29 megawatt, and in case of shortcut distillation column it was also around 29 megawatt. So that is fairly around the same. Distillate rates and the reflux rates are also calculated. For the bottom temperature, bottom rates and boil-up ratios are also calculated. Let's have a look on the stream results to view what are the product compositions. For the top stage product, so 34057, nearly all of the water is leaving from the top stage. But at the same time, 315 kilograms per hour of ethylene glycol is also leaving. Let's compare the top product of the shortcut column and the RADFRAC column. So in the shortcut, we had calculated 67.02 kilograms per hour of ethylene glycol in the top product, and now it's much more than that. We can determine the recovery of the ethylene glycol in the top product. So 315.72 by 67021.4. So this time around 0.4% instead of 0.1% of ethylene glycol is leaving from the top product. We can further fine tune the parameters to adjust the minimum recovery of the ethylene glycol or the loss of ethylene glycol in the top product. So that is the calculation with the default parameters. So let's have a look on the other conditions or the input specifications that we can give to the RADFRAC column. For the RADFRAC, the minimum requirements are, if we have the condenser and reboiler both, then we need two specifications. Or if we have no condenser and no reboiler, that is typically the case of the absorber, then we don't need to specify anything over here, because of the degree of freedom for the column specifications over here is 0. But we have to define the feed stage. The product stage is automatically taken from the connection ports. Pressures are defined. Otherwise, we can define the pressure profile. So the pressure profile at the stage 1 should be 0.15 bar. If the pressure at any other stage is also known, then we can define the pressure over here as well as the pressure profile. For the condenser, if there is any subcooling available, then we can define the degree of subcooling. Otherwise, we can leave it alone. We can define a separate utility stream over here. And similarly, in case of reboiler, we can provide a reboiler utility stream if the utilities are defined in the utility section. So these are the minimum requirements for the column specifications. Additional specifications can be provided on this page if we have any design specification or we vary to any parameter to obtain the design specifications. We can define the efficiencies in terms of the vaporization efficiency or Murphy efficiency. These are entirely two different concepts to define the column efficiency. In case of any available efficiency, we can provide the number of stage and the corresponding efficiency in this section, as well as mercury efficiency. So these numbers have to be very carefully chosen in the columns. For the rate based calculations, we don't need to define the efficiencies of the column internals. Additional information, if we are dealing with the reactive distillation or a reaction inside the column in case of absorption, then we can define the reaction starting stage and the ending stage along with the hold up. And for that purpose, we have to define the reaction first. In the reaction section, we can take advantage of the default template for the reactive distillation. So in this section, if we define the reaction as reactive distillation set, it can be taken as automatically in the reaction section over here. We don't need to define anything as of now. Rather, we were asked to define the column internals. So let's have a look on the column internals so that we can define over here. For column internals, the packed column is suggested with the Cockledge FlexiPack packings. So let's add a new section for the column. Open the column internal folder. By default, Aspen Plus helps in defining the column stages as auto sectioning. Auto sectioning can be done based on the feed port and the product draw locations, or we can have the auto sectioning based on the flow rates inside the column. It is convenient to have one rectification section and one stripping section, so that is based on the feed and draw location auto sectioning. So it have provided automatically some of the column internals. Let's change the column internals. If the column internal details are known, then the calculation mode should be rating based. Otherwise, it can be taken as interactive sizing. So the primary difference is in the interactive sizing, Aspen Plus calculates the column diameter to match the approach to flooding of by default 80% number. In the rating based, Aspen Plus takes whatever the column internals are defined and determines what should be the approach to flooding and other operational column feasibility reports based on the rating mode of calculations. So let's shift it to rating mode because we have now the column internal details. It's a packed column. For the packing, there are a lot of available options for the packing. For given case, we are known to have the FlexiPack packing and the FlexiPack provided by the Cockledge vendor. The given specification is it should be metal 1.4x. So this is the column internals, and also the tray spacing and diameters are known. So section height should be 1.5 meter above and 2 meter below. So this is 1.5 meter section height, and the column diameter is the same 4.75 meters. Similarly, below the feed stage, that is the second section, it is also pad column. Packing is FlexiPack by Cockledge. It's a metal 1.4x, and the column and the section height is 2 meter below the feed stage, and the column diameter is the same as 4.75 meter. Since we are not really into the designing mode of the distillation columns, so we'll stick to the preliminary information. We can run the simulation with the given numbers. So the results are available. Let's have a look on the results, specifically on the product purities. So temperatures are more or less the same as previously provided, and The ethylene glycol recovery and the top product is slightly changed from 319 to 315 kilograms per hour. But still, apparently, this is quite a lot of loss of ethylene glycol in the top product. We can fine tune the parameters in the design specifications. What happens uh, as we increase the reboiler duty, it further volatiles the heavier component than water and increase their loss in the top product. So we can adjust the reboiler duty to lower the loss of heavier component in the top product. We can do the same automatically using built-in feature of design specification. But before that, let's have a look what other informations are available in the column internals. When you open column internals, it provides the details of the two sections. For example, what we have provided the section details. You can also look on the design parameters. If any of the design parameters is required to change, for example, the pressure drop calculation method or the pressure drop per unit packed height default values, then you can adjust over here. Some packing constants are also provided over here. The same information can be available from the further subfolder, and results of the section can be obtained from the same folder. So the column section 1 starts from stage number 2 to stage number 3 because stage number 1 is the condenser and feed enters at above stage 4. So only 2 stages are included in this section, and below feed stage the second section is given. The column diameter is specified, packed height per stage is also given, section height is 1.5 meter. So there are 2 stages for this 1.5, so the per unit stage the height is 0.75. The maximum capacity is given 56% is approach to the system limit. Capacity factor, section pressure drop, and other valuable informations are given. Stage by stage numbers are also given, and if there is any mandatory information available, then it should be provided over here. For example, the liquid load is below 2.44 cubic meter per hour per square meter, so it should be up to 2.44 for the most feasible column operation. The most valuable information over here is the hydraulic plot, so that gives indication of the column operational feasibility. So by default, if all the number of stages are given in the blue color, so that is the feasible operation. So here the vapor and liquid traffic at each stage is also provided, the actual condition of every stage operation, and correspondingly in the packed case the pressure drop across each stage is given as a function of liquid flow rate and the vapor flow rate. So if the operating point is in between the limits, that means the column can be operationally feasible with the given rating based or given packings. And the complete column hydraulic details are given over here. So where for the both sections the pressure drop per section is given, the approach to flooding is given. So this limit should be less than 80% in normal circumstances for the feasible column operation. Otherwise, if the limit is higher than 80%, then jet flooding can happen and column may not be operationally feasible. You can also view the details. It will take back to the column sections and you can view the results by stage. And similarly, for the second section, you can view the results by stage. So these are the internal details of the distillation column. So one pending task is we have to reduce the ethylene glycol loss in the top product. That can be done by adjusting the reboiler duty and specifying the recovery. So let's first use the built-in feature of column design specification, create a new section where we have to decide the mass purity, the mass recovery of 0.996 or 99.96% water recovery in the top product, and the component to be defined as a recovery as water, and it should be in the top product, and feed is taken as the same of F2. We don't have to decide anything over here, and that can be obtained by varying any one of these two specifications by adjusting the reflux ratio on the or the reboiler duty. The feasible option is we can adjust the reboiler duty. So conceptually, if we want to reduce the ethylene glycol loss in the top product, then the reboiler duty should be less than 24. So that will reduce the vaporization of ethylene glycol and similarly the loss of ethylene glycol in the top product. So let's vary the reboiler duty. We can pick the option of reboiler duty, and we have to provide the lower and upper bounds. Let's adjust from 20 megawatt to 25 megawatt. We can give a maximum step size agar we can rely on the predefined values. So the results are very quickly available. It iteratively varies the reboiler duty to adjust the recovery of water in the top product. So let's have a look on the stream results now. So the mass flow rate of water is now it's adjusted to 99.96%. Previously it was very close to 100% recovery of water in the top product. So the reboiler duty should have been reduced, but the more important is ethylene glycol loss is very close to the acceptable limit. It's 1.59. So we can calculate what is the percent loss. So for that purpose we can take, this is 1.59 by 6702 1.4. So this is very negligible. So this is very negligible loss, and the purity of water can be checked. It's 99.995%. So that is very much appreciable number as of now. So what is the result of the reboiler duty now? It's 23.73 megawatt compared to the previous number. So results can also be checked from this option where we have defined the variation. We have defined the lower bound from 20 to 25 and the final value is 23.73. So this is the number at which the water recovery is justified along with the minimum loss of ethylene glycol in the top product. So you can check the remaining results, particularly the boil up rate, boil up ratio, bottom rate, and the top product. Same can be verified from the profiles as well. It gives a complete profile from the stage number 1 to the last stage. In total, we have 8 stages. For every stage, how the temperature builds up from the condenser temperature to the reboiler temperature. We have provided a fixed pressure at the condenser, so it hasn't calculated much of the pressure drop. So duty of the reboiler and condensers are given. Condenser is 28.8 and reboiler is 23.73. The liquid and vapor flow rates at every stage are also calculated. Then the feed stage, at feed stage we have total molar flow rate of 2278.4 kilomoles per hour. That is the feed, and similarly the product stages are also given. Additionally, we can check the enthalpy and flow rates. More important is we can check how the composition varies from stage 1 to the last stage, where at the last stage or close to the reboiler water composition and at the top water compositions are given. If we want, we can also plot the composition. Let's plot the composition of water and ethylene glycol at every stage. So this is how the mass composition of ethylene glycol and water changes. The water composition is increased from 0 to the final value in the top product, and ethylene glycol varies from the maximum to the minimum values. So this is how we can plot different compositions. You can also check the vapor compositions on mass basis or mole basis. You can also check the K values that indicate the separation feasibility, or even the complete column hydraulics, including temperatures, flow rates, the density, viscosity, and other very important indices, including the surface tension or foaming or the vapor pressures. So these are the minimum informations we have to have as of now. In the future session, we'll be working on the absorption stripping section of the CO2. Then we'll discuss the rate-based calculations, how to simulate the rate-based systems. This feature analysis feature is also very valuable. We won't be digging into the analysis feature. In a future session, we'll work on this to see how the column analysis can be performed using this analysis feature. So let's move on to the second purification section, where we have to separate monoethylene glycol from the remainder ethylene glycol products. So let's continue with the second distillation column. The second distillation column is related to the purification of monoethylene glycol from the glycol products. So since monoethylene glycol is the lighter component of ethylene glycol products, it will be received from the top product, whereas the diethylene, triethylene, and tetra-ethylene glycols will be received from the bottom product. So the specifications provided for the monoethylene glycol column is: use the equilibrium based column calculations, number of stages, reflux ratio, and reboiler duty will be taken from the shortcut model DSTWU. The mole base recovery of monoethylene glycol is 99.99% with the purity of 99.95% mass basis. So that's a difference from the dehydration column. In the dehydration column, we had only the recovery of water, but here recovery as well as purity is required. So we have to have the two well set design specifications in this case. The top stage pressure is also given, that is less than the previous column. For column internals, the two sections are there. One section above the feed stage where the pad column will be used with the same coagulage packings, whereas below the feed stage it's a tray column with the sieve tray and two passes. So these internal column details will be specified. So let's continue with the same simulation. Here we have to define first the shortcut mode, the DSTWU, to determine the minimum design specifications. Then we can use those design specifications for the RADFRAC column. Let's first use a manipulator to duplicate the bottom product stream rich in the ethylene glycol products. Let's call it duplicator 2. From duplicator 2, the feed will be the same as the column 2 product. And next we have to have one DSTWU column. Let's call it shortcut column 2. The feed to the shortcut column 2 will be the same as the reboiler product of the column 1. Let's call it F3. One product stream, let's call it shortcut top 1. It's already named. Let's call it shortcut top 2, and the reboiler product will be shortcut bottom 2. Use the design specification as of the previous practice. Let's use minus 1.3 as the reflux ratio to have 30% more than the minimum reflux ratio calculated by Aspen Plus. Use the ethylene glycol purity of 0.9999, that will be 99.99% recovery of ethylene glycol in the top product. And we can use diethylene glycol as the second specification for the heavier component. Let's use it 0.01. The top stage pressure is 0.125. Let's assume the same as bottom stage pressure. Let's run the simulation. So results are available. For these results, we will have 23 number of stages and reflux ratio is 0.32. And the feed stage is 9 in this case. For the steam results, mole flow of ethylene glycol, it's 99.99% recovery, and diethylene glycol, it's 0.01% in the top product. Mass purity as of now is 99.8%, but we need 99.95%. We can specify it in the RADFRAC column. For other purpose, the reboiler duty, condenser duty, feed stage, and number of stages, reflux ratio are already given. So let's use the RADFRAC column for rigorous simulations. Name it as RADFRAC column 2. Take feed from the duplicator block, name it as F4. We'll need one top product as a liquid distillate, name it as RADFRAC top 2, and one bottom product, name it as RADFRAC bottom 2. So we can use the same design specifications as obtained from the shortcut column. So let's take 24 number of stages, total condenser. Reflux ratio is determined as 0.324, and rather than distillate rate, we can use the reboiler duty. Reboiler duty is 23.23. The feed stage is 9. It's given over here 8.69. So let's use the feed stage of 9, and we can use the pressure as 0.125. So that's a minimum information for the RADFRAC column. Let's run the simulation. Results are available. We can view the results. So the molar recovery of ethylene glycol is nearly 100%. Let's have a look on the purity. The purity is 99.5%. So we have to work on the purity. Molar recovery can be reduced slightly less than the 100%. Before design specifications, let's use the column internals as given. Let's open the provided information. So we can use again two sections based on the feed rate and draw informations. So let's shift it to rating modes. That means we are doing the rating with the given internal geometry. The above feed rate, it's a pad column above feed stage. Use FlexiPack. It's Van der Koglitsch, and use metal of dimensions 1.4x. The stage section height is 5 meter and diameter is 5.5 meter. So let's use 5 meter as a section height and 5.5 meter as a diameter. Below feed stage, it's a tray column with the two passes. Default is already taken as one pass. So these are the two passes of the liquid flow. The tray spacing is the default default is taken as 609.6 millimeter. That's a very much common number, but the diameter is 7 meter. We are missing some of the information for the internals. Let's continue from the folders. Otherwise, you can click next to land on the page where the missing information is required. So here this section is empty. That is the center downcomer width. So it's a width of this downcomer at the stage and at the bottom of the downcomer. So that is given as 0.4085 meter. Let's use the same number, 0.4085 in meters. The bottom of the downcomer is taken the same as the top of the downcomer. So with this, the internals are specified. Let's run the simulation. Results are available. We can view the results once again if there is any change in the product purity based on the mass fractions. It's still 99.5%. We can have a look on the hydraulics. So looks like the bottom section has some issues. The issues can be checked from here. So the operating point is very close to the jet flooding. So the operating point of stage 12 is approaching the maximum flooding, maximum entrainment limit of 10%. So that can be slightly worked on. But as of now, let's stick to this warning message and move on to the design specifications. For design specifications, we have to add the two details, recovery and purity. Let's add one design specification as mole recovery. Yeah, recovery is mole basis, and that is 0.9999. So 99.99% ethylene glycol. Choose ethylene glycol should leave from the top product. And the second specification is the purity of the top product, and that purity is based on the mass, and purity should be 99.95%. So it's the same ethylene glycol component leaving from the top product. If we have two design specifications, then we have to have two manipulated variables. So manipulated variables can be one, the reflux ratio given in the operation specifications, and one, reboiler duty. We can use two manipulated variables. Let's use reflux ratio, range it to something from 0.1 to 2, and similarly use another design specification of reboiler duty. Use this to, let's say, from 15 to, let's say, 30. The earlier point was 23 megawatt, so we can move between 15 and 30 megawatt to have a look if these the lower bounds and upper bounds are well within the desired manipulations. So run the simulation. Results are available, however there is a warning. Let's have a look on the warning. So RADFRAC not converts in 25 outside loop iterations. Let's have a look on the control panel, how the convergence was happening. So here is the convergence. It started with the error to tolerance ratio of 207,899 and kept on changing in between. So if this is the case, then one most convenient option is, let's use higher number of iterations that can be changed from the convergence section of the same block. Let's increase to somewhere 200 iterations, and along with this we can give a slight damping to help the solver. Let's flush the previous results and run the simulation once again. So again, The load limit in stage number 1 reflux ratio number stage is less than the minimum number of stages computed. Warning while generating report. Let's have a look. Again in 200 iterations it couldn't fix. One option is let's slightly relax the reboiler duty calculations. So let's change from 10 till 30. So results are available with this. So what happened? In fact, it couldn't figure out the response of the design specifications. One possibility is the solver could not figure out the design specifications inside the upper and lower bounds of the duty and the reflux ratio. So reflux ratio was already stretched enough from point 1 to 2, but apparently looked like the duty requires slightly more flexible lower and upper bounds. So with this, results are available. The new result for the reboiler duty is 25.88 and the reflux ratio is 0.47. So with this, let's cross check once again what are the purity and the recoveries. So this time recovery is adjusted back to 99.99% on mole basis with a slight loss of remaining components, and the loss can be checked from the purification. So ethylene glycol is 99.95% pure on the mass basis in the top product, and the remainders are some of the diethylene glycol, remainder some of the water, and nearly no molecule of triethylene glycol and tetra-ethylene glycol are in the top product. So this is how we can adjust the column specifications, resolve the preliminary convergence issues. So these are not the only convergence issues. You may happen with a lot of other errors, but depending upon the nature of the error, it can be adjusted with the number of iterations, error tolerance, damping level, and also if these are not enough, then further details of the solver facilitations can be added in the advanced section of the convergence. So this is how we have simulated two columns. The remainder columns I will solve them in a very quickly manner, so you can follow the rest of the video to follow the simulation of the diethylene glycol column and the triethylene glycol purification columns. Overall, the simulation approach will be the same. First, use the shortcut column using Fensky Underwood Gilliland or Win Underwood Gilliland method. Then use those design specifications or the preliminary design parameters from the shortcut column as input for the RADFRAC column. Still, keep in mind these are not the optimizations. However, the preliminary simulation results with the provided column internal geometries. Given that we don't have any of the information, shortcut column provides the minimum requirements for the RADFRAC column, and RADFRAC column then can be used in an iterative loop or in a rating mode to get the column internal details, specifically the operational feasibility. Due to the time constraints, we could not cover the details how to fix the column internals or how to design the column. Rather, we have taken the advantage of the provided information of the column internals. If that is the case, where the column design is required, then we can have a separate video, separate session to figure out the column internal geometries. Several rule of thumbs can be used but again this is a very tricky job to design a column. The most appropriate option is assume a geometry, then run it in the iterative mode, in the iterative sizing, and have an eye on the column hydraulics to design the feasibility. So here, as you can notice, some of the column internals are not appropriate, specifically at the bottom. Those messages can be checked from the warnings or from the error messages. So for example, at the last stage, the entrainment at stage 20 was above the specified maximum percentage liquid entrainment of 10%. So for that purpose, we can fine tune the internal geometry and fix this error. Until unless all the hydraulics of the column internals are ensured, and apparently the traffic of liquid and vapors are appropriate on those column internals, the column won't be considered as a operationally feasible column. Then playing between the reflux ratio and number of stages is another task, where the number of stages gives a capital and maintenance, while adjusting the reflux ratio gives a flexibility in the operational feasibility. So having a break even between the operational and capital cost will give an operationally feasible optimum design of the column internals. So the remainder section of this video will be taken in the fast pace. You can follow the video to completely go through how to develop distillation train or the separation scheme for the purification of different ethylene glycol products.